This is the discussion for law of conservation of matter. I also sometimes call it the law of conservation of mass matter, which we'll be talking about here in a second. We're going to specifically talk about balancing equations and then measuring masses in the lab and how that relates to this law. Law of conservation of matter is a cornerstone law for chemistry. We use it all the time. It's used in the future units of our course, so it's really important that you understand this law and understand that we're always using it as a backbone for much of what we're going to learn about later this school year. The general definition is just that mass or matter cannot be created or destroyed. I use both of those words because when we're in a lab, we discuss the law of conservation of matter in terms of mass. The mass of reactants must equal the mass of products. If we have 10 grams of chemical to start with, we must have that many grams of chemical to finish. And then for matter, that's more in terms of atoms, which we talk about on the classroom side of our class. And we're talking about keeping the same number and type of atoms consistent on the left side and right side of a chemical reaction. So how do we go about doing that? Most of balancing equations is more of a skill and more of a practice makes perfect type of concept. There are a few rules though that we are going to follow. So we're always going to balance chemical reactions using coefficients, which just like in math class are the numbers in front of the term, or in this case the number in front of a chemical symbol of some sort. We cannot ever change a subscript. Do not touch subscripts, which are the small numbers beneath the rest of the writing. So for example, in this formula CaCl2, the 2 affects only the chlorine, what's directly attached to, there. In the calcium nitrate here, the 3 affects only the O, but the 2 affects everything inside of the parentheses. So really there are 2 nitrogens and a total of 2 times 3, 6 oxygens. So subscripts only affect what they're directly attached to. On the other hand, the coefficients that we're going to use for balancing affect everything after the coefficient in that formula. And then there's the general tips. These are more of the practice makes perfect. You're going to get used to using these and you're going to get a skill and you're going to become better and better at balancing equations as the year occurs. So I like to start by finding the most difficult looking formula, the one that looks the most complex. Start there. Work methodically, work left to right across the arrow. Start a formula, finish a formula, or start a particle, finish a particle. You're going to want to try to balance in groups if possible. So there are these things called polyatomic ions, such as nitrate, NO3, that you can balance on the left side of your arrow and on the right side of your arrow. That's helpful. And finally, save elements for last. So I'd like to show you some examples of this. Here are 4 problems. And if I'm looking at the first problem, the 2 most difficult looking formulas are the Na3PO4 and the K3PO4. I'm going to start with the Na3PO4 just because it's on the left, and that's typically where I would start reading. So inside of this, I see a couple of different things happening. I see that there's a 3 attached to the sodium, and then there's a 4 attached to the O. However, I also know that this PO4 is a polyatomic ion, and that's something that you just know more by practice. We're going to learn a lot of ions this year, and since it's a polyatomic ion, I can check right away and see if it's on the other side, and sure enough it is. So there's one of those whole particles, and there's a second one over here. So I can balance that as a group. But starting with this first substance, I see that there's sodium and there's 3 copies. So since that's the first particle and there's 3 copies, I need there to be 3 NAs on the right. So I'm going to put a coefficient 3. Again, I can't put a subscript there. That's not allowed. Now, since I put that 3 in front of this NaOH, it's also affecting the OH. Now I also know, and this is coming from practice, that OH is a polyatomic ion. I see the OH on the left side as well. So since I have 3, and then there's OH, 3 OHs, I need to also have 3 OHs over here. So I need a coefficient 3 in front of the KOH. The 3 also affects the K. That makes there be 3 Ks. There's already 3 Ks over here. The last thing of this formula that we didn't check is PO4. There's only one of these. I know there's only one because there's not parentheses with a subscript, so there's only one copy of this. It's only written once. there's one PO4, so this equation is balanced. You could also go and check individual atoms, 3 sodiums, 1P, 4 O's there. This O is separate, 3 O's, 3 H's, 3 H's. A second problem, looking at the most difficult looking formula, to me, the lithium carbonate, the Li2CO3 is the most difficult. There are 2 lithiums, so I need there to be 2 on the right. I'm going to put a coefficient 2. This 2 affects the lithium, but it also affects fluorine. So now there's 2 fluorines, which is good because there's 2 fluorines on the left as well. Finish up this substance methodically. Magnesium, there's 1. And finally, CO3, I see 1 copy of CO3 because there's not parentheses. And there's 1 copy of CO3 on the left as well. So this whole thing is balanced. Number 3, the most difficult looking substance would be the P2O3. Additionally, these 2 are elements, so I want to save those for last. Working left to right across this formula, that's the methodically kind of concept. There are 2 phosphoruses. There's 4 over here, so I would need to multiply this by 2. This 2 affects the P, it also affects the O, so now 2 times 3, common mistake would be 2 plus 3. 2 times 3 gives me 6 O's. I only have 2 O's right here, so to get to 6 divided by the 2 that I have, I need 3 copies. This is a balanced chemical equation. And then finally, problem number 4, this would be my most difficult looking formula, at least to me. I see 1Be, so we're good right there. I see 2 F's, I see 1 F, so I need to multiply by 2. I see 2 RBs, and I see 1, so I need to multiply by 2. Now this 2 affects the whole thing, so there's 2 NO3s, and again, I know that that's a group. You're going to take some time to get to knowing that that's a group, but that's a group. 2 nitrates, there's 2 of the nitrates, so there's 2 copies of everything inside the parentheses, which makes that balanced. It takes practice, so the only way to get practice is to actually practice, but you will get better at balancing equations as the year goes on. In the lab side of the room, we're going to be looking at masses. And it's important to know that mass is always conserved. And then the most common situation that we see this in is in a gas. It's very hard to mass a gas because once gases are formed, they typically leave their container unless you make a concerted effort to try and contain that gas. So here's just a couple examples of how massing a gas or massing substances would be using the law of conservation of mass matter. In the lab, let's say we have a beaker that contains 100 grams, or that is 100 grams, and then there happens to be some water in there with the beaker, and we know the beaker with the water weighs 120 grams. Well, how much is the water? Now that's really pretty simple. We want to take this word water, this word beaker away from the phrase beaker and water. So all we're going to do is do 120 minus 100, and we know that the added amount must be 20 grams of water. Now that's very simple, but that's the basic premise of all these problems in the lab setting. We know that we can't just have magically gained 20 grams of water. It had to have come from somewhere, and that's why that 20 grams came. It's from that water right there. Another scenario would be if we were to take a couple of chemicals and mix them together. Let's say that we have a TT, a test tube that weighs 30 grams. And let's say we have a test tube with baking soda that weighs 35 grams. Well, how much baking soda did we just add? That's 35 minus 30, which of course is 5 grams, just like the previous example. Likewise, if we have a test tube with vinegar and that weighs 32 grams, how much vinegar did we put into that test tube? So 30 minus 32, of course, is 2 grams. Now, we know that we have 2 test tubes plus a baking soda and vinegar, which react, and hopefully you know that forms bubbles. That's a reaction that you probably have done as a kid. And it weighs 65 grams when it's done. Now, if we've been keeping track, we did 35 and 32. So 35 and 32 equals a total of 67 grams. But this says only 65 grams are inside that test tube. hopefully you know that since it formed a gas and it doesn't say anything in this problem that the gas was trying to be collected, that gas must have escaped. So we could solve this in one of two ways. 67 minus the 65 equals, of course, 2 grams. Or since we have two test tubes and each one weighs 30 grams, that's 60. Let's see, 65 minus 60 equals 5 grams of chemical. We had 5 and 2, which makes 7 grams of chemical. 7 grams minus 5 grams equals 2 grams. So either of those methods work. We know that we had 7 grams of chemical, 5 grams of chemical remained, or we had 67 grams of glass and chemical, 65 grams of glass and chemical remained. In either case, 2 grams of chemical is not accounted for, which means it must have formed a gas and it must not have been trapped. So that's the basics of law of conservation of mass matter, both in a balancing chemical equations fashion and in a laboratory fashion of looking at masses and how masses change from before to after a chemical reaction.